Hey guys, this is Professor Janacek, and I'd like to talk to you about the divergence theorem. So to begin with, we'll let D be a connected and simply connected region. Here we are in R3. It's going to be enclosed by an oriented surface S. Now we'll let F be a vector field, and we'll let N be the outward unit normal vector on S. With all of that, then we know that the surface integral, f dotted with n ds, is equal to the regular triple integral over our region D of the gradient dotted with f dv. Now this is really a nice theorem. It's simply a three-dimensional version of the flux form of Green's theorem. This theorem can be interpreted as saying that the net expansion throughout the region D is equal to the flux on the boundary of this region. So this is another example of how this relates to the fundamental theorem of calculus. We can look inside of the region to and relate that to something on the boundary of that region. Again, just a beautiful idea, a great idea. So grateful to have that fundamental theorem of calculus to allow us to expand it in these forms. So let's take a look at an example. We want to compute the net outward flux of the vector field F, defined by the components x squared, y squared, and z squared across the surface S, which is defined as the set of all points x, y, z, such that x squared plus y squared plus z squared is equal to 25. And this surface is a sphere. So first thing we need to do, what we're going to look at, of course, is the surface integral, but we're going to compute it just using a simple triple integral, a regular triple integral. So I'm going to go ahead and build this one piece at a time rather than trying to set up the whole integral. Let's look just at the inside. So let's take a look at what is the gradient dotted with our vector field F. Remember, the gradient tells you to take the partial derivative of the first piece with respect to the first component with respect to x, the partial derivative of the second component with respect to y, and the partial derivative of the third component with respect to z. And then, of course, this is a dot product, so we're going to simply add those. So let's see. Again, I can write this out in notation just as a reminder. This is telling us to take the first partial with respect to x of the first piece plus the first partial with respect to y of the second piece plus the first partial with respect to z of our third component there, which gives us x, let's see, what did that give us? 2x plus 2y plus 2z. All right, so that's going to be our integrand. Now, another thing that I notice is that we're looking at a sphere. Since S is a sphere, specifically x squared plus y squared plus z squared is equal to 5 squared, then let's use spherical coordinates. So that gives us, let's see if you recall, x is equal to 5 sine u cosine v. Y is equal to 5 sine u cosine v. Oh, nope, that's sine u sine v. And z is equal to 5 cosine u. Also recall these parameters. So u will go from 0 to pi. V goes from 0 to 2 pi. Just as a reminder what that looks like. If you've got your sphere, looking at a sphere, however you want to draw that. So U is measuring down here, V is measuring all the way around in the XY plane. So U measures from Z down to Y, V measures from X all the way around on that XY plane. And let's see, and then the R value in this case goes from 0 to 5. And then we also have, remember in spherical coordinates, what is dV? Whoa. dV is R du dr dV. Or you could write it as du, yeah, we'll just leave it in that. Some people write it as du r dr dV. We'll go with this version. Okay, so now I think we're ready to set up our integral. So if we want to compute that surface integral to find that net outward flux, again, this is the flux form. Right, so flux comes from that form there, but we're going to compute this by using a regular triple integral. All right, so this would be the triple integral over our surface D, over the region D, of 2x plus 2y plus 2z dV. So again, notice that del dotted with f is 2x plus 2y plus 2z. All right, so let's go ahead and fill this in. Let's see, this gives us, we've got a triple integral here. We'll fill in what those limits of integration are in just a moment. Writing this in spherical coordinates, I'm going to factor out that 2, and that gives us 5 sine u cosine v plus 5 sine u sine v plus 5 cosine u, and then dV is r du dr dV. So looking at it in this order, we can kind of see now the order that I want to write those limits of integration. U will be the inside, U will be the first one, R will be the second one, and V will be the third one. So we'll work from the inside out. So let's see, U we say goes from 0 to pi. R goes from 0 to 5, and V goes from 0 to 2 pi. Okay, let's see. So we can go ahead now. Let me factor out the 5 and the 2. So I've got 10 times this triple integral. And we're going to integrate first with respect to u. So just be careful. Make sure you're looking at just the u values. So notice the cosine, for example, this first piece, the cosine of v, that's just a constant. So I just need to integrate sine of u, which is negative cosine u. Keep that cosine v on there. The next piece, again, I have a sine u. The sine v will just stay there, so I have minus cosine u sine v. And then finally, integrating the cosine of u gives us, oh wait, by the way, I need to take that 5 out. That's better. Whoa, that's just cosine u. Factored out that 5. So integrating the cosine of u gives us just plus sine of u. And we're going to evaluate this for u going from 0 to pi. So what does that give us? So evaluating at the cosine of pi, and then evaluating at, well, yeah, cosine of pi, sine of pi, and then evaluating at u equal to 0. So that will give us, let's see, just a cosine of v plus sine of v plus cosine v plus sine v. Okay, let me just think about this, make sure that's all right. Let's see. It's -1. -1 positive, so that's all going to work out just fine. And then yeah, watch that subtraction. So cosine of 0, of course, is 1, and then we've got those negatives, but then we're subtracting that, so we end up with a positive cosine. And then, okay, yeah, I'm happy with that. All right, so now we're going to enter, oh, well, actually, we can combine these a little. That gives us 2 cosine v plus 2 sine v in the integrand, but I can go ahead and factor out that 2. So let's make that a 20 out here. And then we just have cosine v plus sine v. And now we're going to integrate with respect to r. I only have that one r in the back, so when we integrate that, we get cosine v. Actually, let's write it down here. I don't know that I'll have room there. Cosine v plus sine v of 1/2 r squared, evaluated from 0 to 5 dv. And that's not an uppercase v, that's just my parameter v. Those are little v's out there, not uppercase v's. Okay, so what does that give us? So 5 squared divided by 2 minus 0, 25 over 2. Factor that out and multiply that by 20. So all I'm doing is evaluating this and then multiplying it by 20. Take your time with that. But what you end up with, let's see, that gives us actually 25 times 10, or 250 times the integral from 0 to 2 pi of cosine v plus sine v dv. And that's not so bad. That gives us 250 times integrating cosine v, we get sine. Integrating sine, we get negative cosine. So it ends up being a subtraction. Evaluate that from 0 to 2 pi. What is that? 250 times 0 minus 1 minus 0 minus a negative 1. Oh, well, look at that. That's 250 times 0, which is just 0. All right there. So the net outward flux on this vector field is 0. Very, very interesting. Enjoy.